Hello, I'd like to begin by thanking the organizers for the opportunity to speak with you today. I'm Tom Sharpton from Oregon State University, and today I'll share our work on how environmental exposures, the collective set of which we refer to as the exposome, shape the gut microbiome and in turn, human and animal health. As has and will be made evident over the course of this conference, we now know that the gut microbiome is central to host physiology. It supports immunity, nutrient metabolism, endocrine signaling, cardiometabolic health, and even behavior. In short, our microbiome functions in ways that promote health and help maintain homeostasis. That said, our microbiome is sensitive to exogenous factors such as changes in diet, administration of pharmaceuticals, or exposure to pollutants. These and related exposures can affect which microbes reside in our gut and influence the overall means through which our microbiome interfaces with physiology. When our microbiome is sufficiently perturbed, a process known as dysbiosis, its functional contributions to health may break down, which can set the stage for various diseases. Collectively, these observations have yielded two critical questions. First, which environmental factors drive dysbiosis? And second, does the microbiome mediate how we experience these exposures? By addressing these questions, we can improve discovery of exposures that threaten key microbiota and also clarify which microbiota or their functional pathways are important targets for biodiversity preservation. As it turns out, these are tough questions to address because the exposome is incredibly diverse and complex. It encompasses every chemical, physical, and biological agent we encounter. Think about the myriad chemicals you're exposed to in a single day, and then layer on all the dimensions of that exposure. Is it acute or chronic? High or low dose? One time or repeated? Each of these factors can change how our bodies and microbiomes respond to an exposure. In short, exposure is vast and multifaceted, and identifying which specific exposures matter for the microbiome is like searching for a needle in a haystack. To address these questions, researchers have traditionally relied on what they know. They use existing knowledge to hypothesize which exposures might matter and then test those ideas in a relatively translationally relevant, but oftentimes expensive model. This approach has revealed important links between exposures and dysbiosis, but it also carries bias and limits the number of leads that we can test. A complementary strategy is high-throughput screening. High-throughput screening systems allow us to rapidly probe diverse exposures and under many different conditions. They've already transformed how we understand chemical and drug toxicity, but they remain underutilized in microbiome science. The key is balance. Screening platforms can efficiently sift through the exposome haystack, but their leads must ultimately be validated in translational models. Enter zebrafish. Our lab has helped pioneer zebrafish as a high-throughput screening resource for the study of how exposure drives dysbiosis. Zebrafish offer unique advantages, such as low-cost husbandry, rapid generation times, germ-free derivation, non-invasive stool sampling, and diverse automated assays. We can grow large numbers of fish in tanks and can even isolate embryos and larval fish in 96-well plates. These characteristics enable using zebrafish for studies to screen for exposures that perturb the gut microbiome. We also know a lot about the zebrafish gut microbiome thanks to the broad international community of researchers that study it. In short, the zebrafish gut microbiome influences physiology in myriad ways, including immunity and behavior. It is sensitive to environmental conditions, and it is robust across facilities. This model system has helped reveal exposure agents that impact the gut microbiome. For example, we showed that exposure to the consumer-grade antibiotic triclosan rapidly perturbs the zebrafish gut microbiome. Additionally, by taking advantage of the rapid growth rates of zebrafish, we were able to show how exposure to different diets affects the assembly and development of the gut microbiome throughout lifespan. And moreover, by leveraging the large sample sizes that zebrafish afford, we showed that combined exposures, for example, rising water temperatures together with an intestinal pathogen, produces unique effects on the gut microbiome that differ from either exposure alone. In other words, the impact of an exposure on the microbiome is context dependent. Well, so far, these and related studies have helped to identify exposures that disrupt the microbiome. But the bigger question is, do these exposure-induced changes alter host physiology, the defining feature of dysbiosis? To explore this, we turn to a persistent organic pollutant called benzoate-pyrene, or BAP. BAP has been linked to behavioral defects in humans, mice, and fish. What's unclear is how it elicits these effects. Because the gut microbiome also influences behavior, we ask, does BAP cause neurotoxicity, at least in part, through the microbiome? To test this, we raised about 550 zebrafish embryos in 96 well plates, exposed them to varying concentrations of BAP, and followed them into the larval zebrafish stage. We then measured behavior using the larval photomotor response, essentially how much the fish moves when a light shining down on the plate flickers on and off, before dissecting the intestines for microbiome profiling. This allowed us to determine whether BAP exposure shifts behavior and whether those behavioral changes track with shifts in the microbiome. Our analysis shows that BAP does alter gut microbiome composition with evidence of a modest dose-dependent effect. But overall, the impact is not dramatic. Only a small fraction of the variation in microbiome composition can be explained by BAP exposure. We see a similar pattern when linking microbiome composition to larval behavior. The microbiome correlates with total movement, but again, the effect is subtle. Taken together, these findings suggest that the microbiome assembly is largely individualized, but that BAP can steer this process, and those microbial shifts are tied to behavior. Importantly, we can only detect these subtle yet meaningful effects because the zebrafish model allowed us to work with very large sample sizes. Based on these observations, we next asked whether BAP affects behavior through the microbiome. To test this, we took advantage of our ability to derive germ-free fish at scale. We exposed both conventionally reared fish, which carry normal microbiomes, and germ-free fish to either 0 or 10 micromolars of BAP, and then measured their behavior. The beef swarm plot on the right shows conventional fish in light color and germ-free fish in dark color. Under control conditions, germ-free fish are more hyperactive than conventional fish. But with BAP exposure, that difference disappears. Conventional fish become more hyperactive compared to their controls, while germ-free fish become hypoactive. In other words, the effect of BAP on behavior flips depending on whether the microbiome is present. This experiment was only possible because of the zebrafish system's ability to enable us to generate germ-free cohorts at scale. And together, these results show that the microbiome both influences baseline behavior in zebrafish and also mediates the behavioral impact of BAP. So let's tie all these threads together. There are a couple important points of discussion to keep in mind here. First is that pinpointing the environmental drivers of dysbiosis is essential if we want to prevent microbiome-driven disease. But it's also worth remembering that dysbiosis may not arise solely from external exposures. Genetics and even a failure to simply acquire the right commensals can play a role. Our efforts to define dysbiosis needs to consider these multiple dimensions and their interactions if we want to create guidelines that mitigate risk in the same way we think about chemical toxicity in exposure science. Second, advancing discovery requires both approaches, knowledge-based studies that are translationally rich and high-throughput systems that allow us to scan broadly without bias. Zebrafish are one powerful solution, but they're not the only one. In vitro systems and other models also have utility and value here. The key is coupling screening with translational follow-up so that we don't miss important leads. Third, zebrafish offers a unique opportunity. As I've shown today, they let us explore how exposures perturb microbiome assembly and even uncover how the microbiome mediates host outcomes, such as the behavioral effects of benzoate-pyrene. But ultimately, these insights need to be validated in more translational models and, where possible, in human populations. That's the direction in which our team is actively working. And finally, by identifying the exposures that perturb microbiomes, we can better guide efforts to preserve microbial biodiversity and protect taxa most at risk. So in short, if we want to move beyond describing dysbiosis and towards preserving microbiome diversity and safeguarding its contributions to health, we need scalable models, careful validation, and a willingness to look at the exposome in all of its complexity. I want to finish by expressing my gratitude to my lab and collaborators for their help in conducting the research I've discussed today, as well as the NIH, NSF, and USDA, who generously supported this work. Thank you.